Hi, my name's Natasha Wright, and I'm a PhD student here at MIT, and I work on water treatment systems. And to get started here, I wanted to talk about a mantra that you hear pretty frequently, and that's that you should work hard, but you should also play hard. But when I was growing up, there was a third part of this phrase, and that was that every single morning, my dad, before I left for school, would say, work hard, play hard, and I had to respond with, and don't forget to ask good questions. And he still does this to this day, and it's so very important. And so I'm going to talk about two different projects today, both in the realm of water, and how asking the right questions to the right people in the right way has really allowed us to find a valuable problem statement and address that in a meaningful way. And so the first question is, how did I get involved in water in the first place, or why am I interested? This is a map of the Ogallala Aquifer, with everything in colored being areas of rapid depletion. My extended family, are farmers in the Midwest, and I remember sitting at the Thanksgiving table in about 7th grade, them talking about this issue and writing a 7th grade report on the Ogallala Aquifer. So that was my first exposure to water constraint. That aquifer supplies 30% of the water to the nation, groundwater to the nation for irrigation. Secondly, I watched the movie Erin Brockovich. It's a little bit older than maybe some of the high school students have seen, but I recommend it. It stars Julia Roberts, and it's about water contamination in Hinckley, California. And so this particular movie was also really inspiring to me. But water quality as an issue in the US, of course, and it's also an issue globally. So there's actually hundreds of devices that have been developed for water treatment in the developing world. I've shown 3 images here. And when I started this project, I had no idea about water treatment technologies. I didn't know what reverse osmosis was, or chlorination, or how these processes worked. But what I found interesting is this figure here. So I was working in India, and this is the percent of the rural population that uses different water treatment methods. And what I found interesting is that 73% of the rural population doesn't treat their drinking water at all, even though there actually is pretty decent access to all of these hundreds of filters that exist. So my question was, why is that? Why should I be looking at these technologies? And so I started talking to people. As everyone, all the inventors here have mentioned, it's very important to talk to all your stakeholders. So I talked to government officials, I talked to nonprofits that both distribute, design, do community outreach. I also talked to the communities themselves. And what I found interesting is that here I'm sitting next to one of those clay candlestick filters, and we're talking about whether or not they actually use this filter. And what people kept telling me is like, well, I use it during the rainy season when the water looks muddy, but not when it's dry season. That's an aesthetic attribute to the water, right? It looks brown. They would also tell me things like, well, I used to use it, but it didn't really make the water taste better. I want my water to taste sweet. And so I was like, what does sweet mean? Because I'm working through a translator for this. And as I moved from community to community, what I ended up finding out is that this whole region had very salty groundwater. And so sweet to them was just the opposite of salty. And since their water was too salty, and they had been given these water purifiers that don't remove salt, they were using groundwater in a filter meant for surface water, and so as a result weren't using the filters. And so because of this, I started looking at the prevalence of groundwater all across India. And I found that over 60% of the land area, everything that is green, yellow, and red on this map, has groundwater that is too salty to drink. And 75% of the rural population uses groundwater, not surface water, as their drinking water source. So that's a pretty big portion of the population that may want to remove salt from the water, and that removing that salt might help encourage the drinking of safe water, as well as the health benefits that come along with that. And so I started looking at desalination. The most common method of desalination using a membrane is reverse osmosis. From your high school chemistry classes, osmosis, water going from the less salty side to the more salty side to equalize in concentrations. Instead, we're applying a pressure to the high salty side, pushing it the other way. This technology requires a lot of energy. There are community-scale reverse osmosis systems that exist in India, but they're unable to go off-grid because of the number of solar panels it requires. The cost becomes economically unsustainable. So I started looking at other technologies, specifically electrodialysis. With this technology, we're applying a voltage, and we're using the current that passes through the anode and the cathode, the 2 electrodes, to remove ions from the water. This technology requires up to 70% less energy, 70% fewer solar panels, and we recover 10 times more water. So the system on the left, as they're implemented currently in the villages, only recover 40% of the water. 60% is wasted, thrown back on the ground. On my system, I can recover up to 95%, so only 5% is wasted. So that's an attribute of the technology as a whole, and what I've been working on is what does it take to take electrodialysis, this old technology, and really make it work with solar power. So because I can apply a DC current and voltage versus AC, what comes out of the wall, I can tie them directly to the solar panels. And we can look at what happens when you have a variable power consumption of your system, depending on the salinity of the water, but also a variable power supply load based on the solar irradiance. And so we're looking at optimizing that problem. The top picture was from the Desal Prize, which was a competition in New Mexico. We won that competition, which allowed us to pilot in Jalgaon, India. The product water from that plant goes to a hydroponics facility. And then now we have a pilot in the village of Chaluru. And we also actually have a pilot going into Israel and then Gaza in the next few months here. And so one of the big questions with these technologies is, one, cost optimization, but also what does it take to run this technology, which does require high voltage and current, in a village setting with minimally trained operators. So those are the types of things we're looking at with the pilot. So let me go back then to the question of these home filters. So that's one of the problems in India. In India, one of the problems is that home filters are given in areas where surface water isn't used and the primary contaminant is salt. That's one of the issues. But these filters are distributed worldwide. So are those filters being used? It's a $24 billion market. Are those filters being used? We have no idea. And so in order to start looking at this question, organizations have done a lot of surveys. But there's something called social desirability bias when you survey someone. And what that means is that you tend to answer in the way that you think you should answer. So for example, if you're at the dentist office and you get asked, how often do you floss? You're likely to say, every day, Mr. Dentist, Mrs. Dentist, Dr. Dentist. And instead, and the same thing with your high school teachers, right? Huh, did you do that reading assignment? Of course, right? And it's the same thing. I give you a filter. You're not going to tell me you don't use it. You'd make me feel bad, right? And so surveys really don't work in this context. And so what we've tried to do is develop a sensor that actually fits within the tap handle. It doesn't touch the water. And it monitors when the tap handle is being elevated and depressed, and logs that data over the course of an entire year, and transmit that back to either the donor organization, the filter manufacturer, the NGO that's distributing it, to know if we're putting our money in the right places. Are our education programs working? Are people using these filters every day or not? And that's the question we're trying to answer with this particular device. So I would like to thank Lemelson, especially my advisor, Dr. Amos Winter, as well as the crew that helps get both of these projects going, both in my lab and friends, Sahil, David, Sterling, Dave, and David, and also the variety of funders that have helped out on both of these projects. And so with that, just a reminder to make sure you're working hard. Nothing beats those late nights, and you can't go without them. Also to play hard, but really to make sure that you ask questions and you understand what types of answers you're getting and when you need to push back on those answers. So with that, I'll open it up to questions.
Do we have any questions? Oh, yeah, right there in the middle.
With your electrodialysis being a little bit older technology and your application of this, is there a higher limit of salt concentration for this process? And I guess what I'm leading to, can it do salt water?
Can it do seawater?
Yeah.
Yeah. You can use electrodialysis on seawater desalination, for seawater desalination. It will not be the most energy and the best energy and optimal way of doing it. So you actually should use reverse osmosis or a thermal technology for desalination. Electrodialysis works much better for groundwater desalination when the salinity level is 5 to 10 times less than that of seawater. It's possible, though. You can do it.
Any other questions? Okay, we will move on then.